Welcome to this walkthrough of LeetCode problem number 1178, titled Number of Valid Words for Each Puzzle. In this session, we will explore the problem statement, analyze the challenges, and discuss various approaches to solve it effectively. Let's dive in. In this problem, you're given two lists, a list of words and a list of puzzles. Each puzzle is a string containing exactly 7 unique lowercase English letters. The task is to determine how many words from the list are valid for each puzzle, based on 3 specific constraints. First, a valid word must contain the first letter of the puzzle. Second, the word can only include letters that are present in the puzzle itself. Finally, the word doesn't have to use all the letters in the puzzle, it can use just a subset. The output should be an array, where each element represents the number of valid words corresponding to the respective puzzle in the input list. Now, let's look at the input and output formats. The words list consists of strings of lowercase letters, and the length of this list is denoted as n. Similarly, the puzzles list contains strings of exactly 7 unique lowercase letters, with its length denoted as m. For the output, we return a list of integers, where each integer corresponds to the count of valid words for the given puzzle at the same index. To better understand the problem, let's review an example. We are given the words list containing AAA, ASIS, able, ability, act, actor, and access, and the puzzles list containing abaves, abridas, absolute, absuras, actresh, and gasixes. The output for this input is the array 1, 1, 3, 2, 4, 0. For the first puzzle, abaves, the only valid word is AAAA because it contains the first letter and all of its letters are present in the puzzle. For the second puzzle, abridas, the valid word is again AAAA. For the third puzzle, absolute, the valid words are AAAA, ASIS, and able. These examples illustrate how the constraints determine whether a word can match a particular puzzle. Continuing with the explanation, for the fourth puzzle, absuras, the valid words are AAAA and ASIS since they satisfy all the constraints. For the fifth puzzle, actresh, there are 4 valid words, AAA, ASIS, act, and actor. Finally, for the sixth puzzle, gasixes, no valid words exist. This happens because none of the words in the list can meet all the constraints for this puzzle. These examples highlight how the constraints play a crucial role in determining the output for each puzzle in the list. By systematically checking each word against the rules, we can compute the number of valid words for any given puzzle. Now, let's look at another example to further solidify our understanding. Here, the words list contains apple, please, and please, while the puzzles list includes elwixes, elkses, elpsxi, selpxi, and zelpsi. The output for this input is 0, 1, 3, 2, 0. For the first puzzle, elwixes, no valid words exist. For the second puzzle, elkses, the only valid word is apple. For the third puzzle, elpsxi, the valid words are apple, please, and please. For the fourth puzzle, selpxi, the valid words are please and please. Finally, for the fifth puzzle, zelpsi, no valid words exist. The constraints ensure that only words fitting the puzzle's rules are considered valid, and this example also emphasizes the importance of efficiently handling edge cases, such as when no valid words exist or when input sizes are large. By keeping these constraints and edge cases in mind, we can design an optimized solution for the problem. To start, let's consider the brute force approach. The intuition here is straightforward. For each puzzle, we iterate through all the words in the list and check if the word can be formed using the puzzle's available letters. While doing so, we must ensure that the first letter of the puzzle is included in the word. For every word that satisfies these conditions, we increment the count of valid words for that puzzle. However, when implementing this, we encounter a significant challenge. With n words and m puzzles, this approach involves nested iterations, leading to a time complexity of O(n*m*k), where k is the average length of a word. This makes the approach impractical for large inputs, as the operations grow rapidly with the input size. The key limitation here is the computational expense caused by iterating through all possible word puzzle pairs, making it unsuitable for efficient processing. Now, to address the inefficiency of brute force, we turn to an optimized approach using bit masking. The key idea here is to represent both words and puzzles as bit masks, where each bit corresponds to a letter of the alphabet. This allows us to use integer operations instead of string comparisons, which are much faster. With this representation, we can quickly check whether a word is a subset of a puzzle by performing bitwise operations. Additionally, we focus on two key conditions. First, the word's bitmask must be a subset of the puzzle's bitmask, and second, the word must include the first letter of the puzzle. To further optimize, we generate all subsets of the puzzle's bitmask, excluding its first letter, and match these subsets against the word bitmasks. By pre-computing the bitmasks for all words and storing their frequencies, we can efficiently calculate the count of valid words for each puzzle. The complexity now becomes n plus m asterisk 64, where 64 comes from the 2 to the power of 6 subsets of a 7-letter puzzle. This is a significant improvement, making the approach highly efficient for large inputs. Given the limitations of brute force, bit masking emerges as the chosen strategy due to its superior performance. By reducing string comparisons to integer operations and leveraging subset enumeration, we achieve a solution that is both time-efficient and scalable for large datasets. While this approach does require additional memory to store the pre-computed word frequencies, the trade-off is well worth it for the performance gain. The implementation of subset generation adds some complexity, but the benefits far outweigh this cost. In conclusion, bit masking is the optimal solution for this problem, as it efficiently handles the constraints and provides a practical way to deal with large inputs without excessive computational overhead. In this problem, we are tasked with determining how many words from a given list can be formed using the letters from each puzzle. There are two critical constraints to keep in mind. First, all the letters in the word must be present in the puzzle, and second, the first letter of the puzzle must be included in the word. To solve this, we can start by considering a brute force approach. This involves iterating over every word puzzle pair to check if the word satisfies the constraints. First, we parse the input by identifying the list of words in puzzles, and we initialize a result list to store the counts of valid words for each puzzle. This setup lays the foundation for our brute force algorithm. Now, the brute force approach progresses by iterating through the list of puzzles. For each puzzle, we extract its first letter, which is critical for the constraints, and convert the puzzle into a set for efficient lookups. We then initialize a counter, count, to keep track of how many words from the list are valid for the current puzzle. For each word, we also convert it into a set of characters and check two key conditions. First, the word must contain the first letter of the puzzle, and second, all the letters in the word must be a subset of the puzzle's letters. If both conditions are met, we increment the counter. Once all words have been checked against a puzzle, we append the count to the result list. At the end of this process, the result list contains the number of valid words for each puzzle, which we return as the output. To better understand the problem, let's break down some key insights. The constraints of the problem rely heavily on subset and membership checks. For example, we use X and Y to check if the first letter of the puzzle is present in the word in set_A.isSubset, set_B, to verify that the word's letters are all contained within the puzzle's letters. These set operations are efficient and save us from performing character-by-character comparisons. However, the brute force approach has a significant computational cost. If n represents the number of words, m represents the number of puzzles, and k is the average length of a word or puzzle, the time complexity of checking all word puzzle pairs is n*m*k. This might work for small inputs, but as n and m grow, the approach becomes computationally expensive and impractical for larger datasets. The choice of data structures plays a crucial role in implementing this algorithm effectively. Sets are the backbone of this solution because they allow efficient membership and subset checks, which are essential for verifying the problem's constraints. By representing both words and puzzles as sets, we can leverage these operations to simplify our logic and avoid unnecessary computations. Additionally, a list is used to store the counts of valid words for each puzzle. This result list serves as the final output of our algorithm, where each element corresponds to the number of valid words for the respective puzzle in the input. To optimize the brute force approach, there are several strategies we can implement. First, we can pre-compute representations for words, such as bitmasks or sets, to avoid redundant conversions during each iteration. This saves both time and computational resources. Second, we can filter out invalid words early by checking if a word contains letters that don't appear in any puzzle. Such words can be skipped entirely, reducing unnecessary iterations. Lastly, since the first letter of each puzzle is mandatory, we can pre-filter the word list to only include words that contain this letter. These optimizations together significantly improve the efficiency of the algorithm. Finally, it's important to consider edge cases to ensure our solution is robust. If either the list of words or puzzles is empty, the output should be an empty list. Words that are longer than puzzles or contain letters not found in any puzzle can be skipped directly, as they can never satisfy the constraints. In cases where there are duplicate words or puzzles, we need to handle them appropriately to avoid incorrect counts. Additionally, when dealing with single-letter words or puzzles, we must verify that the constraints are still met, as these cases can behave differently from longer inputs. Addressing these edge cases ensures that our solution works correctly for all possible inputs. Here, we start by importing the counter class from the collections module, which will help us efficiently count the occurrences of word patterns. Inside our solution class, we define the main function, findNumberOfValidWords, which takes in two lists, words and puzzles. To process the data, we first define a helper function called get_bitmask. This function calculates the bitmask representation of a word, where each bit corresponds to a letter of the alphabet. By iterating through the characters of the word, we use bitwise OR operations to set the appropriate bits in the bitmask. Next, we create a counter object to store the frequency of each unique word bitmask, which is derived by applying the get_bitmask function to all words. This allows us to efficiently check how many words correspond to specific patterns later. After that, we initialize an empty list called result to store the number of valid words for each puzzle. Then, for each puzzle, we calculate the bitmask of its first character, which is critical since the first letter must always be included in any valid word. We also compute the bitmask for the entire puzzle. Using these, we prepare to iterate through all possible subsets of the puzzle's bitmask, enabling us to check every combination of letters that could form valid words. To iterate through the subsets of the puzzle's bitmask, we use a while loop. The key here is that each subset represents a specific combination of letters from the puzzle. Within the loop, we check if the subset includes the first letter of the puzzle using a bitwise AND operation. If it does, we add the count of words corresponding to the current subset to the total, retrieving the count from our word_count dictionary. After processing the current subset, we update it to generate the next subset by removing one bit and ensuring it's still a valid subset of the puzzle's bitmask. Once the loop ends, we handle the special case of the empty subset, which represents no letters selected from the puzzle. If the first letter of the puzzle is present in the puzzle's bitmask, we add the count of words corresponding to the all-zero bitmask. Finally, we append the total count of valid words for the current puzzle to the result list. Once all puzzles are processed, we return the result list, which contains the number of valid words for each puzzle in the input. Here, we start by importing the necessary libraries and defining the findNumberOfValidWords method. The goal of this method is to determine the number of valid words for each puzzle. We use a hash map called wordFrequency to store the frequency of bitmasks representing words. A helper function, getBitmask, is used to convert each word into its corresponding bitmask, where each bit represents the presence of a letter in the word. Next, we iterate through the words array, calculate the bitmask for each word, and add it to the map. To optimize performance, we only include words with 7 or fewer unique letters since puzzles are limited to 7 characters. After processing the words, we initialize a result list to store the number of valid words for each puzzle. The core logic begins with iterating through each puzzle. For each puzzle, we calculate the bitmask and isolate the bit corresponding to the first character, which must be present in any valid subset. Now, we focus on iterating through all the subsets of the puzzle's bitmask. By using a while loop, we systematically generate each subset. For each subset, we check if it contains the first character of the puzzle using a bitwise AND operation. If this condition is met, we look up the subset in the wordFrequency map and add its count to the total. The expression, subset 1, and puzzle bitmask ensures that we move through all possible subsets efficiently. Once this loop is complete, we handle the special case of the empty subset. If the first character of the puzzle is present in the puzzle's bitmask, we add the frequency of the empty subset, which is stored as key 0 in the map. Finally, the total number of valid words for this puzzle is added to the result list. This approach guarantees that all subsets are checked while adhering to the constraint that valid subsets must include the puzzle's first character. The implementation concludes with the getBitmask helper method, which calculates the bitmask representation of a given word. This method initializes a bitmask to 0, then iterates through each character of the string. Using a bitwise OR operation, it sets the bits corresponding to the letters present in the word. The bitmask is then returned, providing an efficient way to represent the unique characters of a word or puzzle. With this method in place, the solution efficiently processes both the words and puzzles arrays, leveraging bitwise operations to minimize computational overhead. The final result list, containing the count of valid words for each puzzle, is returned as the output of the find number of valid words method. Here, we begin by analyzing the given input words and puzzles. In this example, the words are AAA, Azus, able, apple, bale, kangaroo, and the puzzles are above C, above can, apple pies. The first step is to compute a bitmask for each word, representing the set of unique characters it contains. For instance, the word AAA has only the character A, so its bitmask is 1 in decimal, or 0000001 in binary. Similarly, Azus includes the characters A and S, so its bitmask is 513, represented in binary as 0001000000001. Words like able and apple include more characters, leading to bitmasks of 8197 and 34833, respectively. Notice that words sharing the same unique characters, such as able and bale, will have identical bitmasks. Additionally, the word kangaroo contains a completely different set of characters, resulting in the bitmask 191621112. At this point, we also tally the frequency of each unique bitmask, which gives us a dictionary 1, 513, 1, 8197, 2, 34833, 1, 191621112, 1. This count will be crucial for efficiently matching words to puzzles in the next steps. Now, we process each puzzle, starting with above C. The first letter of the puzzle is A, which has a bitmask of 1. We also calculate the bitmask for the entire puzzle, which is 2097665 in decimal, representing the unique characters of B, O, V, E, and S in binary. The goal is to iterate through all subsets of this puzzle bitmask, ensuring each subset includes the first letter A. For each valid subset, we check if it matches any word bitmask in our pre-computed word_count dictionary. For above C, the valid subsets include 1, matching AAA, 513, matching Azus, and 8197, matching both able and bale. Adding up the counts from word_count, we find 1 plus 1 plus 2 equals 4 matching words for this puzzle. Next, we evaluate the puzzle above can, which coincidentally has the same puzzle bitmask of 2097665. Again, the first letter is A, and the valid subsets include 1 and 8197. This time, the total matching words are 1 plus 2 equals 3. By systematically iterating through subsets and checking for matches, we efficiently determine the number of valid words for each puzzle. Finally, we turn to the third puzzle, apple pies. Here, the first letter is still A, with a bitmask of 1. The puzzle bitmask, however, is different, calculated as 34833, representing the characters A, P, L, E, I, and S. As before, we iterate through all subsets of the puzzle bitmask, ensuring each subset includes the first letter A. Among these subsets, the valid ones that match our word_count dictionary are 1, corresponding to the word AAA, and 34833, matching apple. When we sum up the counts, we find 1 plus 1 equals 2 valid words for this puzzle. With all puzzles processed, the final output is 4, 3, 2, representing the number of valid words for above C, above can, and apple pies, respectively. This concludes our solution walkthrough, showcasing how bitmasks and subset iteration enable an efficient approach to solving this problem. To understand the time complexity of this solution, we need to break it into distinct steps. First, consider generating bitmasks for the words. For each word, we iterate over its characters to compute a bitmask that represents its unique set of letters. Since words are composed of at most 26 letters, the time complexity for processing one word is proportional to its length, denoted as L_W. If there are n words in total, this step requires O(n*L_W) time, where L_W is the average length of the words. Now, moving to puzzles, each puzzle has exactly 7 characters, and calculating a bitmask for a puzzle is constant time, O(1). With M puzzles, the time required for this step is O(m). Another crucial operation is iterating over all subsets of a puzzle's bitmask. As each puzzle contains 7 characters, there are at most 2 to the power of 7 subsets, which equals 128. This means generating and processing subsets takes constant time per puzzle, O(1), and across M puzzles, this step also contributes O(m) to the complexity. Next, for each subset of a puzzle's bitmask, we check 2 conditions. Does it include the puzzle's first character, and does it match any pre-computed word bitmask in the dictionary? These checks are efficient. The subset validation is straightforward, and the dictionary lookup for word bitmasks is O(1) on average. Since a puzzle has a constant 128 subsets, validating all subsets for one puzzle takes constant time, O(1). For M puzzles, this adds another O(m) to the total time complexity. Combining all these steps, the total time complexity becomes O(n*L_W) for generating word bitmasks, plus O(m) for processing puzzles and their subsets. Therefore, the overall time complexity is O(n*L_W plus M. In practical scenarios, because the average word length L_W is small and each puzzle has a fixed size, this algorithm achieves excellent efficiency. Turning now to space complexity, the first component to analyze is the storage of word bitmasks. We use a dictionary, word_count, to store the frequency of each unique bitmask generated from the input words. The theoretical upper bound on unique bitmasks is 2 to the power of 26, as there are 26 letters in the alphabet, but in practice, the number of unique bitmasks is far smaller and depends directly on the input. For n words, this dictionary requires O(n) space, assuming each word contributes a unique bitmask. For puzzles, we compute the bitmask and subsets for each one. The subsets are generated on the fly, and since the maximum number of subsets for a 7-character puzzle is constant at 128, the space required for subsets is O(1) per puzzle. Finally, we store results for all M puzzles in a list, which requires O(m) space. These 3 factors, word bitmask storage, temporary subsets, and the result list, contribute to the overall space complexity. When we sum up the space requirements, the total space complexity is O(n plus M). This is dominated by the storage of the word bitmask dictionary, word_count, and the result array for puzzles. To compare with a brute force solution, a naive approach would involve checking all n words against each of the M puzzles. This would result in a time complexity of O(n*M), which becomes infeasible for large inputs. The optimized approach, on the other hand, leverages bitmasks and pre-computes word frequencies, reducing the time complexity to O(n*L_W plus M). By limiting the subset generation to a fixed 128 operations per puzzle, the current solution achieves a significant improvement. This optimization is particularly impactful when the number of words in puzzles is large, making the algorithm scalable and efficient. Finally, let's delve into the mathematical justification for the big O analysis. The cornerstone of the optimization is the use of bitmasks, which transform the problem of word and puzzle matching into efficient bitwise operations. These bitwise checks operate in O(1) time. Additionally, subset generation for puzzles is bounded by 2 to the power of 7, or 128 subsets, which is a constant. This ensures that subset processing is fixed and does not grow with input size. Dictionary lookups for word frequencies also operate in O(1) on average, making the algorithm highly efficient. For the best-case scenario, where all words have unique bitmasks and puzzles are sparse, the complexity is O(n plus M). In the average case, with reasonable distributions of words and puzzles, the complexity remains O(n*L_W plus M). Even in the worst case, where all words share the same bitmask and puzzles generate the maximum number of subsets, the complexity does not exceed O(n*L_W plus M, thanks to the fixed subset size. This demonstrates the robustness and scalability of the solution. When solving this problem, there are several common mistakes to watch out for. First, forgetting to enforce the first letter condition can lead to incorrect solutions. The puzzle's first letter must always be present in the word to qualify as a valid match. If you skip this check, you may end up overcounting invalid words. Next, relying on inefficient brute force is another common pitfall. Directly iterating through each word puzzle pair results in an O, an asterisk M, time complexity, which becomes computationally expensive and fails for large inputs. Another issue is improper letter frequency checks, such as using unordered collections or not ensuring that all the letters in the word exist in the puzzle. This can lead to false positives if some required letters are missing. Lastly, overcomplicating bit masking is a frequent source of errors. Bit masking is powerful but requires careful implementation. Misunderstanding how to represent words in puzzles using bit masks can lead to convoluted logic and missed combinations, ultimately skewing your results. Additionally, ignoring edge cases is a frequent oversight. Examples include empty word lists, puzzles with repeated letters, or single-character puzzles. Failing to account for these scenarios can lead to runtime errors or unexpected outputs. To address these challenges effectively, there are several insights worth noting, especially in interview settings. Bit masking is one of the most efficient techniques for this problem since it enables quick set comparisons by converting words in puzzles into compact representations. Pre-computing word bit masks and grouping them by frequency can further optimize the solution, allowing for faster lookups when processing puzzles. It's also important to focus on the problem's constraints, such as the requirement that the first letter of the puzzle must be present in the word. Constraints often provide critical hints for deriving an optimal solution. While brute force might seem straightforward, using optimized approaches like bit masking demonstrates a deeper understanding of trade-offs in time and space complexity. Lastly, discussing edge cases during interviews shows thoroughness and helps ensure your solution is robust. Now, let's look at related problems and alternative approaches. Some problems that are conceptually similar include LeetCode 784, letter case permutation, and LeetCode 320, generalized abbreviation, which involve generating combinations or subsets. Another example is LeetCode 1239, maximum length of a concatenated string with unique characters, which also requires careful handling of constraints. When considering approaches, brute force is the most basic method, where you check each word against every puzzle. While simple to implement, its time complexity of O, an asterisk M, makes it impractical for larger datasets. Bit masking, on the other hand, is a far more efficient alternative. By representing words in puzzles as bit masks, you can use bitwise operations to perform quick comparisons. This approach reduces time complexity to O, n plus m times 2 to the power of k, where k is the maximum number of unique letters in a puzzle, typically 7. However, bit masking does require a deeper understanding to implement correctly, making it slightly more challenging than brute force. Another alternative to consider is a tree-based approach. In this method, you build a tree structure for the words and traverse it for each puzzle. This can be particularly useful if there are shared prefixes among the words, as it allows you to process multiple words efficiently. However, the time complexity for this approach depends on the length of the words and the specific constraints of the puzzles. While a tree can be a powerful tool, it is generally more complex to implement compared to bit masking. Choosing between these methods ultimately depends on the problem constraints and the trade-offs you're willing to make. Bit masking tends to be the most popular choice for this problem due to its balance of efficiency and implementation feasibility, but it's always good to understand other options, especially when preparing for interviews. Thank you for joining this session on solving LeetCode problem number 1178, number of valid words for each puzzle. We reviewed the problem, discussed approaches, and highlighted key takeaways. Keep practicing and exploring new challenges to strengthen your problem-solving skills. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!